Dear students, today in this lecture, I'm going to explain about the energy of an harmonic oscillator. In the last lecture, we already discussed about simple harmonic motion and what is meant by an harmonic oscillator. So here, we will try to explain about the energy of harmonic oscillator. Okay, so in general, harmonic oscillator possesses two type of energy. It's a potential energy and kinetic energy. So potential energy means which is due to the displacement from the main position. You know the harmonic motion means a system which execute a to and from motion about a mean position. So the displacement from the mean position, there is an energy is called potential energy. Then due to the velocity of each at any instant of time, the system has a kinetic energy. So at any instant, the total energy is the sum of these two energies. It's kinetic energy plus potential energy. As we know, for a conservative system, the total mechanical energy always a conserved quantity. That's kinetic energy K plus potential energy K plus U is equal to total energy is a conserved quantity. So suppose let the displacement of an harmonic oscillator, the displacement of an harmonic oscillator at an instant t is given by a we know the displacement of an harmonic oscillator is equal to x is equal to a sine omega t plus phi. So suppose I find the velocity. Velocity is the first derivative of x dx by dt. It's nothing but a into omega into cos omega t plus phi. So the derivative of x. So we know in the previous lecture we already find that velocity is equal to omega into root of a square minus x square. So then from this velocity I can find the acceleration d square x by dt square is equal to minus a square omega minus a into omega square sine omega t plus phi is nothing but minus omega square a sine omega t plus phi is nothing but x, so minus omega square x. From this forces we know from Newton law F is equal to ma. So mass into acceleration is equal to minus m omega square x is equal to minus kx. So minus kx is k is equal to m omega square. K is equal to m omega square. If the oscillator displays through a dx distance, suppose the oscillator displays at a distance dx, then work done on oscillator. So you know the work is equal to force into displacement. So force here, the restoring force, it's almost equal to kx dx. So restoring force, we have to do to work against the restoring force. So it's kx into dx is the displacement. So this work is stored as a potential energy. So if it is placed from x is equal to 0 to x is equal to x, the total work done w is equal to integration of dw, it's equal to kx dx. So kx integral become half kx square. So this work done is stored as a potential energy. So the potential energy of an harmonic oscillator is u is equal to half kx square. It's very important expression. So the next point is to find the kinetic energy. Kinetic energy is, you may know, for a mechanical system of mv square, v is the velocity. So we know v is equal to, in terms of omega, root x square minus x square. So take a square is equal to omega square s square minus x square. So this is the expression for the velocity. So the total energy is equal to kinetic energy plus potential energy. So just adding these two energy together. So the kx square term will cancel. The remaining term is equal to half k square, where a is the amplitude of the system. So it's a constant for a particular motion. So maximum amplitude is always a constant. So half k square is a constant value. So it means total energy is always a constant one. So here E is proportional to a square. So it means the motion will continue to infinite period without the decreasing the amplitude. With if in the case of provide no damping or for damping force of such as frictional force are acting on the system. That's important result is the energy is always proportional to a square. So the next important thing is the graphical representation of these equations. So we know the potential energy expression U is equal to half kx square. If I plot a U potential energy along y-axis and x along the displacement along x-axis, then I'll get a parabolic curve corresponding for half kx square. So the this value is equal to plus a, and this is corresponding to minus a. So the same way the kinetic energy curve, kinetic energy is equal to half k square is a constant one and minus x square. So minus half kx square. The resultant equation is equal minus half kx square with a constant half kx square. So that is equal to a inverted parabola. So this is minus a and plus a corresponding. This so kinetic energy along x-axis, sorry y-axis, and displacement along x-axis. We get a inverted parabola for kinetic energy. The total energy curve is nothing but it's a constant because half kx square is everything is constant, so it's a constant line parallel to the x-axis. Here y-axis is total energy E and x-axis is displacement. So all these curves are put in a single graph, then it will come in this form. This yellow line corresponding to kinetic energy and the black line corresponding to potential energy curve, and the green is the total energy curve. So this is the energy diagram for an harmonic oscillator. You want to remember this diagram and the expression for potential energy and kinetic energy. So at a turning point, that is a plus A or minus A, the kinetic energy becomes zero because when oscillating, when it reaches to maximum amplitude, it will stop there and it will come back to the original position. So the kinetic energy is equal to zero at the turning point, and there the total energy become kinetic energy plus total energy, potential energy. So kinetic energy is equal to zero means potential energy is equal to kinetic energy. Is equal to half kx square. From there I can find a expression for a 2e by k. Root 2e by k is the expression for amplitude. The same way at equilibrium position, kinetic energy become total energy because potential energy equal to zero there. So the displacement equal to zero at that position. So kinetic energy is, from this I can find an expression for maximum velocity is equal to root 2e by 1. So in other intermediate point other than the plus a or 0, or the total energy is partially kinetic energy and partially potential energy, but their sum that is equal to total energy is always half kx square. So this is all about the energy diagram and energy expression for the harmonic oscillator. The next thing is that the kinetic energy and potential energy is varying about the displacement and the time. So I can find the average value of kinetic energy and potential energy. So it's very easy. Kinetic energy average is equal to 1 over t 0 to t integral k dt. K is kinetic energy. So what is k? Half mv square. So 1 over t 0 to t integral of mv square, where v is we have a value a omega cos omega t plus 5 because x is equal to a sin omega t plus 5, and take a v is the first derivative, so it become a omega cos omega t plus 5. Substitute here, and half m is common, 1 over t is common, a square, it's v square, so equal to a square omega square cos omega t plus 5 dt. So that remaining term, the m a square omega square by 2t, I take the out of the integral, and 0 to t cos square theta I can written as 1 plus cos 2 theta by 2. In that form I wrote this expression. Then I took the integral 1 and integral of 1 is become t, and integral of cos theta becomes sin theta by theta. Sin 2 theta becomes sin cos 2 theta becomes sin 2 theta by 2 theta. So I substitute integral limit value from 0 to t is equal to 2 pi by omega. While substituting t is equal to 2 pi by omega, this uh, for t I substitute t itself, and sin 2 pi by 5 instead of here t substitute 2 pi by omega, omega will cancel. The ring it becomes sin 5 minus sin 5, it becomes sin 0, sin 5 minus sin 5 is 0. So only t terms are will be remaining. So m a square omega square t by 4t, t will cancel. So average kinetic energy I have an expression for 1 over 1 by 4 k a square. The same value for I get it for average potential energy. So average potential energy I can here find 1 over t 0 to t u dt, where u is the potential energy. So you know the potential energy expression is equal to half kx square, and x we know as sin omega t plus 5. Find the x square value and take the sine square theta form. So 1 sine square theta is equal to 1 minus cos 2 theta by 2. I took a k square by 1 of 4 t out, then integral become t is equal to sine 2 theta by 2 form. Then apply 0 to t integral, the same will come, t is will remaining, so it is 1 over k square. So average potential energy become 1 by 4 k square while applying the limit. So the final result here I am going to state that average kinetic energy of harmonic oscillator is equal to average potential energy. So both are the same, 1 over 4 k square. Then the expression for, so what we have done in this class is the expression for kinetic energy is equal to half kx square, potential energy is equal to half kx square, and kinetic energy is equal to half k square minus x square, and the total energy is equal to half kx square is a constant, and the energy diagram, so you please remember this diagram, and the find the turning point expression for a and maximum velocity. Then later we have found the kinetic energy and potential, average kinetic energy and potential energy expression. We have proved that both are same, is having the value 1 by 4 kx square. So please go through these notes and you try to derive this once more, and you get in a good idea. And please go through this diagrammatic of the energy curve is very important in the point of view of exam. So thank you.